Welcome you all. In this class, we'll discuss about the interval estimation. We know that the theory of estimation consists of two parts. They are point estimation and interval estimation. The point estimation we have already discussed. Now we will discuss about the interval estimation. What's the meaning of this interval estimation? This can be made clear from the following explanation. Suppose we regress consumption expenditure on income. The regression will give the marginal propensity to consume. Say, if we regress consumption expenditure on income, we will get a coefficient or beta 2, beta 1 plus beta 2 xi, ya equal to beta 1 plus beta 2 xi plus ui is the econometric model for consumption expenditure and income. Consumption expenditure as independent variable and income as the independent variable, and the beta 2 will give the marginal propensity to consume, and this beta 2 will give a single figure, and that is known as the point estimation. Say it equal to 0.6. It is a single estimate and it may differ from the true value. It may be equal to the true value if we repeat the estimation, or it may be equal to the true value in the repeated sampling estimation, but it may not be equal in the single case. But instead of relying on this, and the reliability of this point estimator is measured through the standard error, and instead of relying on this single point, we can construct an interval around the point estimator, then within 2 or 3 standard error on either side of the point estimator. That is, instead of relying on the point estimates alone, we may construct an interval around the point estimator. That is, within 2 or 3 standard errors on either side of point estimator, such that this interval has 95% probability of including the true parameters. That is, we may construct an interval on the expectation that the estimated value may lie within the estimated value may be equal to the true value by about 95% within this confidence interval. That is, the reliability of point estimator is measured by the standard error. Instead of relying on the point estimate alone, we may construct an interval around the point estimator, say within 2 or 3 standard error on either side of the point estimator, such that this interval has 95% probability of including the true parameter value. This is the interval estimation. That is, we construct an interval around the point estimator. Then we are making it sure that it lies or it is closer to the true value. This is roughly the idea behind the interval estimation. That is, how close is say beta 2 cap to beta 2? That is, how close say beta 2 cap to true beta 2? For this purpose, we try to find out two positive numbers, dou, delta and alpha, where alpha lies between 0 to 1, such that the probability that the random interval beta 2 cap minus dou and beta 2 cap plus dou contains true beta 2 is 1 minus alpha. This is the constructed interval. That is, we want to find out how far beta 2 cap is closer to beta. For that, we are constructing an interval. For that, we introduces two positive number, dou and alpha. This dou, alpha lies between 0 to 1. The intervals are beta 2 cap minus dou and beta 2 cap plus dou. Then the probability that beta 2 cap equal to true beta can be explained as probability of beta 2 cap minus dou less than or equal to beta 2 less than or equal to beta 2 cap plus dou, that will be equal to 1 minus alpha. Such an interval, if exists, is known as confidence interval. Here, these two, we assume that the beta 2 estimated beta 2 cap is equal to the true beta 2 by this interval. The estimated beta 2 cap will be equal to the true beta 2 cap will be equal to true beta within this interval. This is known as the confidence interval, and 1 minus alpha is known as the confidence coefficient. That is, this lies between alpha lies between 0 to 1 is known as the level of significance. Alpha is the level of significance and 1 minus alpha is the confidence coefficient. This is the confidence interval. That is our confidence that the estimated beta 2 or the estimator will be equivalent to the true beta 2 lies in between these two intervals. The endpoints of the confidence intervals are known as the confidence limits. That is, here we have two endpoints, beta 2 cap minus dou and beta 2 cap plus dou. Beta 2 cap minus dou is the lower confidence interval and beta 2 cap plus dou is the upper confidence interval. Here our ultimate aim is that it should be an unbiased estimator. That is, the estimated value should be equal to the true value. Then how far it is equal to the true value can be estimated either by the point estimator or by the interval estimator. In the point estimator, we measure this to the standard error. But in interval estimation, we assume that it can be equal to the true value if it lies between these two confidence intervals. There will be two confidence interval limits. One is known as lower confidence interval, the other one is known as upper confidence interval. The interval constructed in such a manner that it has a specific probability 1 minus alpha of including within its limits the true value. That is, this interval estimation is based on the probability concept, and the probability is that 1 minus alpha, and the alpha equal to 0.05 means, or 5% means, that the probability that the random interval shown includes the true beta 2 is 0.95 or 95%. The probability that the interval includes the true beta 2 is 95%. The interval estimator thus gives the range of value within which a true beta 2 lies. That is, the interval estimator explains the range within which the true beta 2 will lie. It doesn't say that the probability of beta 2 lying between given limit is 1 minus alpha, but the probability of constructing an interval that contains beta 2 is 1 minus alpha. It is a random interval, that is, it will vary from one sample to the next. Then, since the confidence interval is random, the probability statement attached to it should be understood in long run sense, that is, in repeated sampling. The interval is random so long as beta 2 is not known. But once we have a specific sample and once we obtain a specific numerical value of beta 2 cap, the interval is no longer a random, it is fixed. As far as beta 2 cap is not known, it is random. If it is estimated, then it is fixed. Now we will estimate the confidence interval for beta 2. We know that with the normality assumption of UI, the OLS estimators beta 1 cap and beta 2 cap are themselves normally distributed with mean and variance. That is, Z equal to beta 2 cap minus beta 2 by standard error of beta 2. The standard error of beta 2 cap is sigma by root of sigma xi square. Then it can be written as beta 2 cap minus beta 2 into sigma xi square by sigma. And similarly, beta 1 cap for beta 1 it equal to beta 1 cap minus beta 1 by sigma of beta. Then this can be written as beta 1 is normally distributed with beta 1 and variance beta, mean beta 1 and variance beta. Beta 2 cap is normally distributed with beta 2, mean and variance. We can use the normal distribution to make the probability statement about beta 2 provided the true variance is sigma square is known. If sigma square is known, an important property of normally distributed variable with mean mu and variance sigma square is that the area under normal curve can be explained as follows. That is, normally distributed variable with mean mu and variance sigma square. Then mu plus or minus sigma explains about 68%, and mu plus or minus 2 sigma explains about 95%, mu plus or minus 3 sigma explains about 99.7% of the area. Sigma square is rarely known and it is determined by the unbiased estimator sigma square. If we replace sigma by sigma cap, then that will be equal to t equal to beta 2 cap minus beta 2 by standard error of beta 2 cap. That is estimator minus parameter by estimated standard error of the estimator. And the t distribution with n minus 2 degrees of freedom can be written as probability of minus t alpha by 2 less than or equal to t less than or t alpha by 2 equal to 1 minus this is the probability limit. This is the confidence interval limit we constructed for the t. Then this t can be substituted by using this equation, that is probability of minus t alpha by 2 less than or equal to beta 2 cap minus beta 2 by standard error, then less than or equal to t, then it will lies between minus 1 minus beta alpha. Then this can be written as follows: beta 2 cap minus t alpha by 2 standard error of beta 2 cap less than or equal to beta 2 less than or equal to beta 2 cap plus t alpha by 2 standard error of beta 2 cap equal to, this is the 100% 100 into 1 minus alpha percent confidence interval for the beta 2. This equal to beta 2 plus or minus t alpha by 2 standard error. Here in this section we'll define the confidence interval for beta 2, that is this can be written as probability of beta 2 minus t alpha 2 standard error of beta 2 cap less than or equal to beta, that is true beta less than or equal to beta 2. These are the two confidence interval, t alpha by 2 standard error of beta 2. This will be equal to the coefficient of confidence interval. That this can be summarized as beta 2 cap plus or minus t alpha by 2 standard error of beta 2. Similarly for beta 1 equal to beta 1 cap minus t alpha by 2 standard error of beta 1 cap will be lies between beta 1 cap less than or equal to beta 1 cap plus t alpha by 2 standard error of beta 1 cap, that will be equal to 1 minus alpha. This is the confidence interval for the beta 1. It can be written as beta 1 cap plus or minus t alpha by 2 standard error of beta 1. The width of confidence interval is proportional to the standard error of the estimate. Larger the standard error, larger is the width of confidence interval. The larger the standard error of the estimator, greater is the uncertainty of estimating the true value of the unknown parameter. The standard error of an estimator is often described as a measure of precision of the estimator. How precisely the estimator measures the true population value. This is the precision of the estimator. Similarly, we can define the confidence interval for the sigma square. Under normality assumption, the variable follows the chi-square distribution with the n minus 2 degrees of freedom. That is, chi-square is defined as n minus 2 sigma cap square by sigma square. Then it will be equal to chi-square 1 minus alpha by 2 less than or equal to chi-square less than or equal to chi-square alpha by 2. That will be equal to 1 minus alpha. Then probability limit can be explained as probability of n minus 2 sigma cap square and chi-square alpha by 2 less than or equal to sigma square 5, sigma less than or equal to n minus 2 sigma cap square divided by square 1 minus alpha 2 will be equal to 1 minus alpha. This is the confidence interval for the. We constructed the confidence interval for beta 1 and beta 2. Here it for beta 2 it follows t distribution, and for the sigma cap square it follows the chi-square distribution.